To proceed, another question is given here, and the question says a gas occupies 200 centimeters cubic at a temperature of 230 degrees Celsius and a pressure of 740 millimeters of mercury. So they're saying calculate the volume of the gas at 25 degrees Celsius and 790 millimeters of mercury. So let's just try to capture this information, then be able to proceed. So you're told there's a gas whose volume, and we shall treat this as V1 or our first volume. And our first volume given in the question is 200 centimeters cubic. Okay, and they're telling us that this gas occupies this environment with this volume at a temperature of, so temperature 1 is given as 230 degrees Celsius. And the pressure recorded at that point given as pressure 1 is 740 millimeters of mercury. Because this is the chemical formula of mercury. This they used to measure this volume, this type of pressure. So, and then we are supposed to actually come up with the volume 2, which is not given, and our temperature 2 given as 25 degrees Celsius, and our pressure 2 given as 790 millimeters of mercury. So, this question does not require us to rely on Boyle's law or Charles' law or Gay-Lussac's law or Graham's law of diffusion. Neither do we need to actually focus on the Avogadro's law. So then we shall be able to use what you call the combined gas law. So combined gas law. Combined gas law. Or ideal gas equation. Combined gas law or ideal gas equation. So, and then that law has to tell us that there is a variation in the volume of a particular gas if certain conditions like temperature and pressure fluctuate or change or vary. It says the volume of a given mass of a gas will fluctuate or change if pressure and temperature as conditions under our consideration undergo changes or fluctuate. For example, we are actually getting asked to calculate volume 2. And of course, volume 2 can get obtained. And this volume 2 will slightly be able to change from this first volume because 1, the temperature has changed as the first condition and pressure has as well changed. Temperature has decreased from 230 degrees Celsius to 25 degrees Celsius. Pressure has increased from 740 millimeters of mercury to 790 millimeters of mercury. So the volume of a given mass of a gas or volume of this gas is going to change because temperature and pressure conditions are going to actually change or they have actually changed. So if volume changes, then that means temperature and pressure must also be able to have undergone changes. So combined gas law states that there's a variation in the volumes of a particular gas if temperature and pressure as conditions undergo changes or fluctuate. Now, then this ideal gas equation has this particular type of formula. Pressure 1, volume 1, temperature 1 should be equal to pressure 2, volume 2, temperature 2. So it borrows knowledge from Charles' law where you're supposed to use these temperatures in Kelvin. So you're going to say plus 273. Then you can also say plus 273. So you're changing this from degrees Celsius to Kelvin. So 230 plus 273. So 230 plus 273. That gives us 503 Kelvin. Then that is 25 plus 273. That gives us 298. And of course, 25 degrees Celsius is what we call the room temperature. And room temperature and pressure has conditions 25 degrees Celsius and of course 1 atmosphere as pressure or 760 millimeters of mercury. So we've done the changing of the temperatures from degrees Celsius to Kelvin. So we shall proceed and now be able to use this formula. So let's say pressure 1 is 740, then volume 1 is 200 over temperature 1 is given as 503 Kelvin. Now you use the temperature in Kelvin. It will be equal to pressure 2 790, volume 2 is unknown, then temperature 2 is 298 Kelvin. Correct. So we shall just cross multiply. We are going to have 740 multiplied by 200 multiplied by 298 Kelvin should be equal to 503 Kelvin, okay, multiplied by 790 multiplied by volume 2. So that I will divide both sides by 543 times 790 Kelvin. So 543 Kelvin times 790. So this and this will disappear. So we have volume 2 is equal to, very good. So I need to pick my calculator and plug in these values to get the answer. So I'm going to have 740 multiplied by 200 multiplied by 298. And this is divided by 503, and then as well divided by 790. So our volume 2 is 110.99 centimeters cubic. So you can see, when temperature decreases and pressure increases, that means when temperature decreases, remember, if you look at Charles' law, we said temperature and volume are directly proportional to each other. So that when temperature increases, volume also increases. But when temperature decreases, volume also decreases. So temperature has decreased. So expect the volume to also decrease. Look at this. When you look at Boyle's law, it says that when temperature is constant, the volume of a fixed mass of a gas is inversely proportional to its pressure, or inversely proportional to the pressure that is actually able to get applied on this container containing this gas. So if you look at pressure, pressure has increased. So when pressure increases, volume must decrease. Why? We've said in Charles' law, when pressure is constant, volume of a fixed mass of a gas and the temperature available in that environment are directly proportional. To mean, when temperature decreases, in as far as Charles' law is concerned, the volume is also expected to decrease because volume and temperature are directly proportional. If you look at Boyle's law, he says that the volume of a fixed mass of a gas is inversely proportional to its pressure as long as temperature is kept constant. So that means pressure and volume in Boyle's law of a particular gas are inversely proportional to each other. So expect when pressure increases, volume must decrease. So you have two reasons as to why we actually end up saying that there was a reason as to why we could actually get the volume decreasing. Because as per Charles' law, when temperature decreases, volume also must decrease. And as per Boyle's law, when pressure increases, the volume must also be able to end up decreasing. So this is our answer in as far as that question is concerned.